Now I'm going to ask anybody who can't see the slide after a presentation, please unmute and let me know. As I say, once I start and go full screen, let me check this before I go on. Okay. Once I go full screen, I can't see anything except the slide. So, what are the 3 steps in cardiovascular activity? First, what makes the blood move? The heart is a pump that provides the force, and its action is critical to our survival, so it warrants individual study. The blood vessels are about where the blood goes. How do we distribute it around to every single living cell in the body? And the answer is going to be a branching tube network. In a way, my first thought about the blood vessel system, and really any branching tube system, is that it fills space and it provides a service that penetrates a 3-dimensional space. That's really what the blood vessels do. I think of the blood very much like an ocean current, because 3/4 of the Earth's history, an organism and a cell were the same thing. All living things are made of cells, and they all started out as single-celled organisms. And so the services provided by the ocean water and later by fresh water are the same services that have to be duplicated by the circulating blood when you have this big multicellular organism. Now, blood vessels are going to be classified by size. Since it's a branching tube network, it's going to leave the heart as a great big rounded tube, and it's going to start splitting into smaller and smaller tubes. The initial set of tubes will conduct the blood, divide it up, and put it in the vicinity of every living cell in the body, where it'll enter a vessel where exchange can occur. Supplies can go out to the tissues, wastes can come into the blood. And then it'll enter another sealed tube system, which will be converging into larger and larger tubes on the way back to the heart. So how do we divide up these types of vessels? First of all, we're going to classify them by size and histological organization, and recognize that blood flow is always one way. Only one way. If blood starts backing up, then we're in trouble. If blood, in fact, pauses, if it stops, we're in trouble. We have to continue that blood flow and make it constant. Blood is always, if we take the heart as the reference point, that's where the pressure is generated. It's going to move away from the heart and diverge into smaller and smaller vessels. It's going to enter the smallest vessels, which will change their wall structure in a way that exchange is possible. And then it will return to the heart by converging the small venules into larger and larger veins. Arteries are defined as carrying blood away from the heart. Now, in many cases, people are taught that arteries carry oxygenated blood. That is true only for the systemic circuit. It is exactly the opposite in the pulmonary circuit. So establish the primary definition. Arteries carry blood away from the heart. Capillaries, our smallest vessels, are the exchange, the permeable vessels, where the actual business of the blood is conducted, giving up the supplies to the living cells, oxygen and nutrients, delivering regulatory chemicals like hormones to a specific region, and pulling in those waste products that are routinely manufactured by every living cell, things like CO2, things like ammonia that's generated if you're dealing with proteins and other waste products. But as you leave the capillaries, as that exchange stops, the smallest vessel that's sealed would be called a venule, and you have started the trip back to the heart. So the order of flow from the heart is always arteries, capillaries, and veins. Now we are going to see some special systems where it is not just one tract through a bed of capillaries. A capillary bed may be joined to another capillary bed down the line. It's called a portal system. We're going to see places of flexibility where paths of alternate flow exist, and based on the position of the body or the condition of the vessel, that blood can take one pathway or can take another to reach the same point. Those will exist, but first, fully establish: arteries away, capillaries exchange, veins return. We see the structure of these vessels as similar, even though the thickness of these different layers differ. We do see that they each have 3 layers. The vessel walls have layers called tunica, after the Roman tunic, a wrapping. Intima is that inner layer that's right next to the flowing blood. Media is the central layer, often heavy in muscle cells and elastic cells are present. And the externa is the outer sealing layer of the blood vessel. Because the heart pumps, the greatest pressure is in the exit vessels from the heart, the so-called ejection vessels, and as blood flows through those arteries to smaller arteries to arterioles, it encounters more friction, and as a result the pressure goes down. So we're going to find that arteries, and especially those close to the heart, are thicker due to this increased pressure, and that the walls of the arteries close to the heart are going to have muscle, because the heart pressure is going to make the artery bulge, and then when the valve closes, that artery wall is actually going to constrict on the blood to keep it moving until the next pulse of pressure pushes the blood forward. We're going to see elastic fiber to accommodate that constant flexing, and we're also going to see in the arteries a kind of a rippled structure like an accordion that allows it to flex like this to increase the volume and decrease the volume with minimal wear, minimal stretch on the internal epithelial cells. Now here we have a comparison, and I'm going to get my printer going to direct your attention to what I'm talking about. Here is a region of the body where we've dissected 2 vessels, an artery and a vein. Now, notice the smaller and circular conformation of the artery. That's because it's on the pressure side, and its thicker wall reflects the thicker muscle layer in the vessel. Notice that the vein is an irregular shape. This always reminds me of a right foot. Sometimes it's oblong, sometimes it's flattened. It's dealing with blood at much lower pressure, but its bigger diameter, its bigger area is reflective of a strategy. Make the vein bigger, and so the resistance of this low pressure, the flow of this low pressure blood is reduced. What we see as typical differences are round with a thick wall to flattened or collapsed, or I would just say irregular, with a relatively thin wall. The ripple shown here is that accordion effect of being able to stretch outward and flatten and then fold as it contracts back. Whereas the endothelium of the vein, you'll notice, is very flat. There's no pulsing after we get through the capillary beds, and the flow is fairly smooth. An internal elastic membrane shown here on the artery is absent in the vein. As we say, it's not moving as much as the artery is moving. The tunica media is very thick, dominated by muscle fibers, and these are smooth muscles, so they are packed closely together, and they are also interspersed with a lot of elastic fibers. So the expansion and contraction of the artery is very much reflected in the constitution of this elastic membrane. Whereas over here it's thinner, there is still muscle because we need to control the diameter of the vein. During times of a large of rest, the veins relax, and about 2/3 of your blood is in the veins. But during activity, we increase the pressure. We want to mobilize that. So we basically contract the veins and increase the pressure and get that blood flowing. As a result, we see muscle cells, but we also see collagen fibers, strong support, but not depending on a lot of movement. The external elastic membrane is present in the arteries, again, reflecting their much greater movement. For example, a radial pulse. What are you really doing with a radial pulse? You feel that bump, bump, bump. What you're doing is seeing an expansion of the artery that's shooting down that artery as the heart rate moves. And it's the movement of that artery that produces that tactile pulse that we can feel. The outer elastic membrane is absent in the tunica externa, the tunica media, of the vein. The tunica externa, this outer layer, has collagen to make it strong and still elastic fibers to allow it to move. And we do have collagen and elastic fibers and also a few smooth muscle cells in the vein. So there are a couple of reliable differences in the histology of arteries and veins. If we have a failure of the structure of the artery wall, it produces a bulge called an aneurysm. This is a weak spot. Now, initially, you might just see it as with the heartbeat, it would expand. You'd be able to see it. If it becomes pronounced, it will form something that looks kind of like a little balloon bulging out and retracting as the blood pressure alters. If it becomes pronounced, it can burst and the blood vessel will lose blood. That means that the tissues that are supplied by that artery will be deprived of blood, and you might suffer some tissue death. So we see this circulation pattern and a regular progression of the names. We call the elastic arteries our closest, beginning with the aorta, beginning with the pulmonary trunk. This is a little bit unfortunate that they retain this color coding, which they did to indicate oxygenated and deoxygenated blood. But in fact, if we're looking at arteries and veins, these two are both arteries. The elastic artery shown here has this largest diameter, rippled endothelium, maximum movement, the greatest pressure variation. And as we distribute out, see these branching arteries that are still major vessels, but smaller than the aorta. We see a reduction in size, still a thick wall, but not as much evidence in the cells and tissues of the expansion and pulsing. We go further into the smallest arteries, and we see them with a thin endothelium that's encased in smooth muscle cells. You can see those naked muscle cells on the outside of the basement membrane. This blood eventually flows into a capillary, and in this case we're showing continuous capillaries here and fenestrated capillaries. We'll define those. There are different kinds of capillaries depending on the need for the rate of exchange. Normal tissue has these continuous capillaries which allow oxygen and nutrients to leave, hormones to leave, allows waste to enter the bloodstream. After the trip through the capillary bed or capillary net, we enter veins, and we see these are drawn in a very kind of round configuration. That doesn't agree with what we've just said about the irregular shape of these veins. They're often convoluted or bulged or oblong or flattened. But we see the progression through larger and larger diameters. This difference here to here and here to here is really not enough to illustrate what you see in most locations of the body if you compare an artery and vein. Usually in the similar location of the body, the vein will have a larger diameter, but you see much fewer tissues here that are devoted to expansion and contraction. So we basically just call the small veins venules, to medium size and large veins, and the return to the great return veins, which are the inferior and superior vena cava, and not actually shown here, the pulmonary veins. Capillary structure is shown here, and what we're going to do is change the vessel so that it allows the transport of material across in both directions. You'll notice the typical epithelial structure of flattened cells that are kind of squamous, pancake-like, providing a continuous, tightly bound surface. And when we look at this boundary layer between the outside and the cytoplasm, here we have this boundary layer, and we see the ability to form endosomes by these epithelial or endothelial cells transporting material in. We also expect gates in these cells that allow for the transition of specific ions, as carriers allow the movement of ions, of nutrients, according to their special transport needs. But there are some places where it is critically important how fast the exchange occurs, especially in the region of glands. And that produces a different kind of capillary called a fenestrated capillary. Das Fenster is the window in German, and that's what this comes from, because these capillaries, in addition to having this endosome capability, have actual pores. Notice how the basement membrane is just covering a hole. There's no cytoplasm there. And so materials that are deposited outside the cell can move across that basement membrane directly into the cytoplasm, greatly enhancing the speed of absorption. This is a feature common in the endocrine system. When you dump a hormone from the pituitary gland, you want it into the blood and around the body as quickly as possible. And that's where we find fenestrated capillaries. We also, in the regions of major gland, find this third type, sinusoid, very convoluted. Look at all this surface area. And in addition to the fensters, you see actual gaps between adjacent cells. These gaps would be small enough that blood cells could not get out, except, well, white blood cells actually could, but red blood cells cannot. But materials that are dropped in the vicinity can move in and join the stream of blood flow. So three types, with continuous being the common type throughout the body. Here's a nice micrograph showing you this branching tube network. We are I'm imagining the blood flows in this direction as this small artery goes through, splits to an arteriole, and then since this is a branching tube network, these are basically just different ranks of division. So here's an arteriole, here's a meta-arteriole, here's further divisions, and all of this space of these little windows or these little chambers then are suffused with capillaries all through here. Notice the almost continuous presence of capillaries. Wherever there's a living cell, there has to be a supply, a network. Also, although you notice the branching tube artery here splitting the blood flow and sending it in two major directions, what you notice from the meta-arterioles is the presence of what's called a capillary bed or net. So the capillaries don't have a single path through tissue, but they have a network of connections that produces what's called a capillary plexus or braid. Typically, the capillary plexus will connect one arteriole to a venule and be controlled by a precapillary sphincter, a ring of smooth muscle fibers, and sometimes only two smooth muscle cells will ring the arteriole right in front of the capillary bed. So when they contract, they can squeeze that arteriole closed and deprive that capillary bed of blood. When they relax, blood pressure pushes them open and blood flow is restored. We also see the presence of other elements in capillaries and veins. Sometimes there's an artery called a collateral. Think of this as a bypass. Basically contributes, it provides the capacity for artery blood to cross over through a region of capillary bloods and connect the flow directly to veins. It will maintain circulation and minimize the volume of damage if a single meta-arteriole or arteriole is blocked. When we fuse collateral arteries, we call that an anastomosis. When we fuse an artery to a vein, we call that an arteriovenous anastomosis. That's a big mouthful. We do see the presence of vascular elements. And you think about the growth of the vascular system. How does it grow? It grows much like the root system on a plant, forming new blood vessels, penetrating into new tissues as they grow. This is present during our growth. This is present during healing. You think about a big cut. A big cut, there's some tissue death, but as we begin to repair that, we have to grow and restore blood vessel surfaces through angiogenesis. There is a hormone, the vascular endothelial growth factor, that stimulates this blood vessel renewal, and it begins in the embryo during development, and it basically reacts to damage and inflammation during healing. Factors that affect this angiogenesis or repair are the chemical factors in the vicinity led by oxygen supply. So if oxygen is in low concentration, then that means it's all consumed. And you have to supply oxygen before living cells can regenerate. This is most important. I mean, and what does important mean? Important means you die quickest without it. Where does that happen? In the heart. Deprive a part of the heart of oxygen, and you have a heart event, something that is quickly lethal or damaging. This brings up a whole issue for the blood vessels and why we call it the cardiovascular system. And that's the concept of vasomotion. The presence of smooth muscle cells throughout the system allows us to contract, to react to pressure, to bulging, and to use contraction of smooth muscles to direct or redirect the flow of blood to different regions of the body. So we call it vasoconstriction if we are contracting the smooth muscle cells, and especially when we contract the arterial sphincters and regulate the flow to particular capillary beds. And we call it vasodilation when we relax them and allow them to expand with blood pressure, restoring or increasing the circulation to that capillary bed. Okay, that's enough terminology. Let's look at a figure. Here is the collateral arteries. You notice them connecting here into an arteriole. Notice those that it's completely surrounded by smooth muscle cells, allowing for the constriction, the contraction of that blood vessel. Now, here's a cross-section showing you the endothelium of the capillary and how two cells can form a precapillary sphincter. So we're going to actually see those at the critical junction point. See how this is departing from the arteriole and entering this capillary bed, which is more like a net. This is a collateral, this is a through channel. Notice this allows kind of direct flow and less exchange. This allows an alternate path. So, you basically could cross this capillary bed by entering this, crossing over here, entering here, and ending up over here. So there are multiple paths of flow across this capillary bed. Here is what we call an arteriovenous anastomosis, a sort of a blood bypass without providing the opportunity for molecular exchange. But blood is basically a solution or a slurry that is based on water, and water is heavy. Our body is big. So the pumping action of the heart and the vasomotion of the vessels is not going to provide for all movement. And this is where the particular anatomy of the body provides assistance to blood movement that is far from the heart. This shows a function of the venous system. Veins are consisting of chambers. You'll notice the pointer is traversing a single chamber with valves, all the valves pointing toward the heart, meaning that blood flow will open them in the direction of the heart. But if blood attempts to fall backwards, it will close the valve. So there's a sort of a stepwise progression that is supported by heart pressure and pumping action that moves this from a vein chamber to the next chamber. The valve then closes to hold it there until the next pressure surge and moves it to the next chamber. But there is an additional effect that relates to the skeletal muscle. You'll notice that this major vein is placed between the two lobes or the two bodies of this gastrocnemius muscle. When our muscle is relaxed, it draws away from the vein and allows for open flow, so blood movement could occur. When the muscle contracts, it contracts inward and squeezes this vein. Now, this is force that's being applied to the blood in the vein that does not come from the heart. And because of this vein system, this pressure is going to tighten this lower valve, but as it decreases the volume of this chamber, it will squeeze blood through the upper valve. Now you'll notice this contraction is occurring at the time we're flexing the ankle in a step. So every time we take a step, at the end of that step, at the end of that contraction, we're squirting blood up to that next chamber. So this is a skeletal muscle assist that allows for improving the circulation here in the appendage, the lower appendage, where we have the longest distance to lift that ample blood that's in the foot and the leg all the way back up to the heart for another pumping cycle. Now, we also will notice that if we are relaxed, those muscles are not in use, then it's going to be the heart pumping pressure that's going to move through this system and return that blood. There's a lot more blood in the veins and a lot settled in the lower body when we are at rest. But when we begin walking, that walking action is going to pump on these veins slowly. If we start jogging, if we start running, that pressure assist goes up and basically assists all the way up the scale to maximum blood flow. This is the distribution of blood in a typical cardiovascular system. And you'll notice something here. Look at this. At rest, 2/3 of the blood, 64% is the total. Large veins, the large vein networks of the liver, the bone marrow, the skin, places that are particularly have a particularly high proportion of blood, because the liver, for example, the liver is involved in assessing blood quality and adjusting it. The bone marrow is the site of blood cell production, and therefore it's constantly dumping new cells and assessing old cells. And the skin, where blood flow is involved in thermoregulation, so it's very dense capillary and vein networks. And then finally, the stuff in between, the veins and venules and medium-sized veins. Look at that, 25% of your blood is in those vessels. Now, what does that mean? 2/3 of your blood is in the vein side at rest. That means the entire pulmonary circuit, arteries, capillaries, and veins. It means the entire heart. And it also means the whole arterial system on the systemic side, plus all of the capillaries. At rest, only a third of the blood in your body is in all of those tubes. So it speaks to a kind of a reserve capacity. At rest, we're not needing to move that blood fast, and it pools in the veins. This is a venous reserve because a third of the blood in the heart, in the pulmonary system, and in the arteries and capillaries is enough to keep us alert, awake, actively functioning at rest. But what we're going to do when we need increased blood pressure and more physical performance, we're going to constrict these veins and force this blood into this expanding network. And we're basically going to increase the rate of blood flow, the heart rate, the pumping pressure, the stroke volume, in order to maximize the delivery of oxygen and nutrients under times of maximum performance. We call this the venous reserve. It's completely adequate at rest, the state that you are in now. But it can be called to action and provide us a greater range of physical performance. Now, the movement of blood through our tubular vessels is a physical feature. The principles that are shown on this page affecting the friction, the resistance, and the consequent blood flow through our arteries, veins, and capillaries is basically hydrology, the movement of a fluid through a pipe. This is what a plumber would know, because these are tubes. We don't have really any difference. The difference in these pipes is that they're not iron or copper pipes. They can actually react to blood pressure and blood movement and affect it. But let's look at this. If you double the length of a pipe, leaving everything else the same, you double the resistance. That's pretty simple. But vessel diameter basically affects the flow in a dramatic way. We're going to see the greatest resistance, the most slowing at the surfaces. And we're going to have the least resistance right at the center, where it's all these red blood cells are doing are bumping into each other and moving with the plasma. So the least resistance is going to be at the very center of these larger vessels. So what does length and diameter show? If we double the length, the diameter, 1 centimeter to 2 centimeters, double the diameter, we actually have a much different effect on the flow rate. So if the diameter is 1 centimeter, the resistance is 16. Double that to 2 centimeters, because of the effect on reducing the resistance drops to 1. So here's the picture. As you eject into the aorta, the biggest vessel, it's got the least resistance, the biggest diameter, and its length is going to affect flow, but very minimally. But as you divide up into arterioles, as you reach the capillaries, the smallest diameter, the resistance goes way up. And so it affects flow of the blood and the consequent flow of red blood cells by slowing them. Turbulence is produced when you don't have a solid open pipe. So what you see here is a plaque deposit that restricts the diameter. Now there's going to be much higher pressure produced here as this blood is pushed against it. And the pressure is going to accelerate the blood as it moves through here, and as it comes out the other side, it's going to spin. This is turbulence. So this restriction will often send signals that require the heart to beat faster and pressure of the blood to increase. Increased blood pressure is sometimes a signal, an indication of blocked blood flow at some critical point. Now, this brings in a series of graphs, and I have to admit, when I never thought very critically about how blood moves through these blood vessels on its trip from the aorta back to the vena cavas or the pulmonary artery around to the pulmonary veins. But once I saw these, it kind of made sense. You think about a pump, you don't imagine if you move through a pipe and it slows down as you get to the middle of the pipe, you expect it to keep slowing down as it moves toward the end. Well, it turns out in our body, there are changes to the speed of movement, and on the backside, on the vein side, sometimes it speeds back up. Let's look at some of the properties of the overall vascular system. And in this, we are looking at the physical space between the aorta on the left, at the origin, and on the far right, the vena cava, with the categories of blood vessels shown, and the vessel diameter. We start with the biggest vessel, 2.5 centimeters is around an inch for the aorta, and that diameter, as we branch through the elastics, muscular, and arterioles, we reach such a small diameter that we are talking about a millimeter or less for the smallest arterioles. Of course, as we said, the capillaries are the smallest blood vessels of all. Purple is where all of the exchange is occurring. And when you enter blue, you'll notice those venules. There is a slight increase in that diameter because the lower pressure, an increase in diameter will lower the resistance. But as we merge these venules to veins and eventually to the far right origin, the vena cava, we increase that diameter again. In fact, above the 3 centimeter mark that is shown in this figure. If we look at the area that these parts of the system, we have the lowest area, and that also means for any length, like 10 millimeters, centimeter, the lowest volume in the elastics. As we branch, that volume and cross-section goes up through the musculars and goes up greatly to the arteries. We have the most cumulative cross-section area in the capillaries. And this makes sense. What does this mean? This means increased surface area. This means more membrane exposed to the flowing blood for the oxygen and nutrients to get out of the capillaries and for the waste products to get in. As we come back into the venules and we seal those vessels off, no exchange. Now, as we're converging these venules, and very quickly the cross-sectional area in total drops off as we get to larger and larger veins, and eventually to the large cross-sectional area of the vena cava. Now, these physical properties will work on the blood pressure. The exit pressure, there's that systolic pressure, 120 millimeters, and it's decreasing as we start to branch through the elastics and through the musculars. And we still have a significant blood pressure in the 50 millimeter range of blood pressure in the arterioles. We enter the capillaries at a lower level, around 40 to 38 millimeters, and it decreases as it flows across the capillaries, decreasing steadily. The friction of the veins, going venules, veins, and vena cava, leaves it at a lowest pressure, right here where it's re-entering the heart. And as we saw with the previous heart diagrams, that's a low pressure, 10 millimeters, as a reasonable average for that returning blood. But this one surprised me, the velocity of blood flow. If we look back at that pressure, as the pressure continues to decrease here, you'd expect it to continue to slow down. But look what happens. The blood comes out at its highest rate from the heart as a response to the direct contraction of the ventricle and that push. And as it branches and goes through the friction of that increasing surface area through the arterioles, it slows way down in its velocity and reaches a slow, steady flow through the capillaries where the surface of the capillary, the total surface area is highest. But as you get into the venules, now you're converging. The pressure is continuing to go down but the diameter is increasing, lowering the resistance. And therefore, the larger veins cause the blood to actually accelerate away from the capillary beds and achieve a pretty reasonable flow rate, up back up here to 14. After we got down to 2 or 3 centimeters per second in the capillaries, it's going to accelerate back up to around, what? My one eye isn't helping here. Maybe up around 17 or 18 centimeters per second as it gets back to the vena cava and re-enters the heart. Of course, the pulse side, the artery side, isn't a constant pressure. It's oscillating between the systolic maximum and the diastolic minimum. So as those valves open and close, this is why our pressure cuffs measure systolic and diastolic pressures, as this on the pressure side is most pronounced in the elastic and musculars, and being kind of here, down here in the arterioles. See how it's diminished and damped out as it enters the arteries. So this is why we put our pressure cuffs on up in this region in order to measure this pulse pressure. Now, this mean arterial pressure is something that we calculate because it isn't simply the pumping pressure, the systolic pressure that's important. It's how completely and synchronously the heart relaxes. And so we calculate mean arterial pressure, or MAP value, to reflect that that second estimate of blood pressure and its effectiveness. So down here through capillaries, we're getting steady flow and a decrease in the pressure, which drops off dramatically as we go through the veins on our return trip and reach a minimum value of pressure, not of velocity, but of pressure as it re-enters the heart. Now, pressure and resistance are always going to interact, and this is an excellent place to stop this recording. So I'm going to stop the show, stop the recording, and end